Imagine a world where artificial intelligence wasn't just science fiction, something locked away in labs. Picture the early 2000s. Suddenly, AI, specifically machine learning, it wasn't just a theory anymore. It actually started walking off university campuses and, well, right into the heart of global business. It was a huge shift. In this deep dive, we're going to unpack exactly how machine learning made that critical leap. How did it go from this theoretical curiosity to being part of our everyday business infrastructure? We'll explore the breakthroughs that made it possible and then journey through its adoption. Think finance, healthcare, e commerce, advertising, all transformed. And we'll get into some real world case studies. Things you use every day, maybe without realizing it, like the spam filter in your email. Seems simple, right? But it was revolutionary. Or those recommendation engines that seem to know what you want next. These really showed ML's practical power. It wasn't just innovation, it was integration. AI became indispensable. So today we'll look at the tech shifts, the specific ways businesses used it, and those early demos that proved it could actually work commercially. We'll also touch on the core ideas that made it all happen. Let's get started on this journey exploring how the future kind of just became the present.
It really is remarkable, isn't it, how a field that was for so long, mostly academic, focused on theories and possibilities, how it suddenly found its feet in the commercial world. That period, the early 2000s, it really represents this maturation. It was a moment where the science breakthroughs met the right conditions, the perfect storm, really, for real-world use.
That's a great way to put it. A perfect storm. So let's dive into those foundations. We kind of have to go back to the beginning of neural nets, right? To the perceptron. It caused a huge stir initially, didn't it? Tell us about that early promise and then, well, the crash.
Oh, absolutely. The perceptron, which was a very early single-layer type of neural network, definitely arrives with a lot of hype, a lot. Researchers like Frank Rosenblatt, well, one source says they were making wild claims,
Yeah.
in interviews with big outlets like the New York Times, saying perceptrons would soon be doing incredible things, translating languages, space travel, even exploring planets. It really captured the public imagination, this idea of machines learning like us.
Wow, space travel. That is pretty wild. It sounds like the kind of vision that would grab headlines. But if it was so promising, what happened? What put the brakes on all that excitement?
Well, that initial exuberance, it got seriously dampened, maybe even killed off for a while, by Marvin Minsky's work. His critique, especially in the book Perceptrons with Seymour Papert, was devastating. People often say it single-handedly killed off enthusiasm for neural networks for more than a decade.
Hmm.
And the core problem they pointed out was a fundamental limit. Early perceptrons could only solve relatively simple or linear kinds of problems.
Okay, linear problems. Can you break that down a bit? What does that mean in practice? Like an example.
Sure. Think about classifying emails. If you can draw one straight line on a graph to separate, say, spam from not spam based on just one feature, like how many times the word free appears, a perceptron could maybe handle that. It does, as the source puts it, only a single multiply and add operation from input to output. Very basic. But what if you need a curved line? Or what if you need to look at how multiple features interact, like sender reputation and certain keywords and link structure? The single-layer perceptron just couldn't do it. It was too simple for the complex, messy problems researchers actually wanted to solve. And that limitation led straight into what people called the AI winter for neural networks. Funding dried up, interest faded, disillusionment set in.
Okay, so big vision hits a hard wall, leading to this AI winter. But obviously, neural nets didn't just disappear forever. How did the field get past Minsky's critique and eventually arrive at what we now call deep learning?
Right, the story definitely didn't end there. The tide started turning back in the 1970s, actually, though it took quite a while for the impact to be felt widely. Researchers figured out how to train networks with multiple layers. Think of it like stacking those simple perceptrons. These deep networks were the real game changer. Why? Because they could perform a chain of operations. The output from one layer feeds into the next layer as input. This lets them learn extremely complicated mappings from input to output. They could essentially draw those complex, curvy lines that Minsky said were impossible for the single-layer versions.
Okay, stacking layers makes sense. But how did they actually train these deeper, more complex systems? What was the key technique?
The secret sauce, really, the crucial technique, was backpropagation. Researchers like Yoshua Bengio were key in developing and promoting this. It's the method that allowed these multi-layered networks to learn effectively. Imagine you feed an input in, the network spits out an answer, and it's wrong. Backpropagation figures out how much each connection, each weight in every layer contributed to that error. Then it adjusts those weights, working backwards, layer by layer, so the network does better next time. It's this iterative adjustment process that lets deep networks learn really intricate patterns from data. It unlocked the whole thing.
So the algorithms themselves matured, getting past those early limits. But you mentioned a perfect storm earlier. An engine needs fuel, right? And a road to run on. What were the other big forces that let deep learning jump from the lab into industry?
Exactly. A brilliant engine isn't much use without fuel and infrastructure. The industrial leap for ML absolutely depended on two other huge trends happening at the same time. First, the data explosion, and second, the revolution in computing power. Let's talk data first. The late 90s, early 2000s, we saw this unprecedented thing we now call big data. Everything started getting digitized. Pictures, documents, music, videos, transaction records. Plus, sensors are ubiquitous now on your phone, your car, smart homes, factories, all generating this continuous massive flood of data, more kinds of data, often better quality data too. And crucially, it was digital data, machine readable.
Right. It's like society itself digitized, creating this massive playground for algorithms. We went from having carefully curated small data sets to just oceans of information flowing constantly.
Precisely. And this ocean of data became the lifeblood for machine learning. Finally, algorithms could be trained on the large data sets they needed, and these data sets were readily available. Yeah. Think about your social media feed today. Deep learning powers that. And it's trained on our collective behavior, right? Every click, every like, every comment, every share, that's all training data. It fuels this constant loop, refining the models. Without that sheer volume of data, even the best algorithms would have just stalled.
And having all that data is one thing, but you need the muscle to actually process it. That brings us to computing power, the hardware side of the revolution.
Absolutely critical. Advances in computing power were just as important, maybe even more so initially. Training deep networks, especially really deep ones, takes a phenomenal amount of computation. That was a major bottleneck for years. But by around 2015, people were building models with well over 100 layers. That just wasn't feasible before.
Yeah.
It really shows how much engineering and hardware matter.
Uh-huh.
The big breakthrough here was using graphics processing units, GPUs. They were originally designed for video games, for rendering graphics quickly. But it turns out that parallel processing is exactly what you need for training neural networks. Later came specialized chips like Google's TPUs. This made training huge models practical. You could distribute the training across many GPUs, drastically speeding things up. Same for using the trained model, what we call inference.
So it wasn't just faster computers, it was specialized computers, almost custom built for the math involved in deep learning. And when you put it all together, the better algorithms, the massive data, the specialized hardware, what did that fundamentally enable? What was the core capability that unlocked?
Well, Ajay Agrawal, Joshua Gans, and Abhi Goldfarb have this great framing. They argue these advances in AI were primarily an advance in the statistics of prediction, end quote. What ML really did was dramatically reduce the cost of predicting things. Suddenly, it became cheap and feasible to make predictions about all sorts of things. So ML found uses not just where prediction was already important, like finance, but also in completely new areas, predicting what's in an image, predicting the path of a self-driving car. These became possible because the cost and capability of prediction fundamentally shifted.
Okay, the algorithms mature, data explodes, compute power catches up, the perfect storm indeed. It makes sense how ML could then move into industry. Let's talk about where it hit first and made a big splash. Finance seems like a natural fit, always looking for an edge with predictions.
Finance was definitely one of the earliest and most significant adopters. And one killer application right away was fraud detection. Before ML, fraud detection was mostly rule-based. If transaction is over $6 amount and from country Y, flag it. But clever fraudsters just learned the rules and work around them. ML systems were different. They could learn subtle patterns in normal transaction behavior from vast amounts of data. Then they could flag transactions that deviated from that norm, even if they didn't break any specific predefined rule. They could spot anomalies much faster and more accurately than humans sifting through millions of transactions. It saved banks a fortune.
I can totally see that. Moving from simple rules to understanding complex patterns. Huge advantage. And it wasn't just catching fraud, right? ML also changed how banks assessed risk, like deciding who gets a loan.
Oh, absolutely. Credit scoring was another major area. Traditional methods used a fairly limited set of data points. ML allowed for a much more holistic assessment. Imagine a neural network taking in, as one source describes, very long lists of data. This could be demographics, age, location, etc. Financial info, income, bank balances, stocks,
Right.
but potentially also an enormous body of social media data. What posts you like, groups you're in, who you follow. This hypothetical smart credit system could analyze all these diverse inputs, find hidden correlations, and output a very precise risk score, like 550. much more granular than before.
Whoa, incorporating social media data into credit scores, that sounds incredibly powerful, maybe a little unnerving too. But it also brings up a question. If the system is crunching all that complex data, how do you know why it gave that score of 550? Especially for something so important like a loan. Sounds like a black box.
You've hit on a really critical issue, one that the field still grapples with today. Opacity, or the black box problem. As one source bluntly puts it, no particular point in the network can be said to mean anything in particular. It's the network as a whole that's telling the bank something. You get this highly accurate prediction, potentially, but without a clear, step-by-step explanation of how it arrived there. This lack of interpretability is a major challenge. How do you ensure fairness? How can someone appeal a decision if you can't explain the reason? It's a huge deal in high-stakes areas like finance.
Right, so there's this tension between predictive power and explainability. Given that challenge, how did they ensure the models were actually accurate and reliable, even if the why was fuzzy? What steps did they take?
Well, the mathematical foundation for training these models, specifically the choice of the loss function, became extremely important. The loss function is what tells the AI how wrong its predictions are during training. It guides the learning. For instance, using something like a log-loss scoring function instead of a simpler Breyer score makes the AI much more sensitive to be overconfident when it's wrong. It pushes the system to not just be right most of the time, but to also assign probabilities more accurately, especially for rare events like fraud or default. So, while you might not always know why, you can mathematically optimize the system to be as accurate and reliably calibrated as possible. Precision was key.
Okay, that makes sense. Focus on rigorous mathematical validation, even if intuition is hard to come by. Now, moving from finance to another critical area, healthcare. Digitizing records was a start, but how did ML take things to the next level?
Healthcare is a fascinating case. Digitization itself was huge, making records accessible, enabling doctors and patients to make faster and better decisions. But ML, especially computer vision teaching computers to see, showed huge potential for improving healthcare. Think about analyzing medical images, things like MRIs, CT scans, microscope slides. While some landmark studies, like diagnosing prostate cancer from MRIs or lung cancer from slides, came a bit later, maybe mid-2010s, the underlying ML capabilities allowing that were really developing through the 2000s. These systems started reaching and sometimes even exceeding human expert performance on specific diagnostic tasks, spotting things radiologists might miss or doing it much faster.
Machines outperforming doctors. That's pretty mind-blowing. Sounds like a huge leap. What about using ML beyond just diagnosis? Did it start impacting treatment or even surgery?
Yes, absolutely. One really exciting area was using ML to reveal relationships between genes, diseases, and treatment responses. By analyzing huge data sets, genomic data, patient histories, how they responded to different drugs, ML could spot patterns invisible to humans. This held the promise of truly personalized medicine, tailoring treatments based on your specific genetic makeup and predicted response. And then there's robotics. Robots, guided by sophisticated ML for precision, started showing potential as more accurate and reliable surgeons than humans for certain procedures. They could enable precision, miniaturization, and smaller incisions, leading to less blood loss, less pain, quicker healing, really transformative potential.
Wow, personalized medicine and robot surgeons. It sounds like science fiction becoming reality. But does this mean the human doctor becomes obsolete? Or is it more like AI becomes a superpowered assistant?
That's a really important question, the human-AI collaboration aspect. And the consensus, certainly from the sources, is that even with very advanced AI, human specialists remain absolutely vital. Take medical imaging again. The radiologist still determines the images for a given patient, decides what needs scanning. They still perform interventional radiology using their judgment to guide procedures. They communicate the meaning of images to primary care doctors, translating the AI's probabilistic output into something clinically actionable. And critically, humans train the machines, especially when new imaging technologies come along. So it's really ML as a powerful complement, augmenting human skills, not replacing them.
That makes sense. Enhancing, not replacing. Okay, let's shift gears to something we interact with constantly, e-commerce. How did ML totally change online shopping? It feels like websites know what we want before we do sometimes.
E-commerce was definitely one of the most visible areas transformed by ML. It was all driven by, as one source puts it, the ability of this data to help people reduce uncertainty and know more about what is happening. This powered the whole recommendation revolution. You land on a site, and it's already suggesting things you might like. It moved beyond just finding what you search for to actively anticipating your wants.
You mean like those people who bought this also bought things, or when the homepage is full of stuff that feels weirdly specific to you? How did companies like Amazon take this prediction game to the extreme?
Exactly those kinds of features. And companies like Amazon started thinking really radically. With prediction getting so accurate, they explored shifting from the standard shopping then shipping model to a potential shipping then shopping model, actually sending items to customers before they even ordered them based on predicted demand. Now that's a bold move. It shows incredible confidence in the predictions, resolving the dilemma of managing inventory and returns by just getting really, really good at reducing uncertainty about what you'll want. It's a prime example of ML not just improving a process, but enabling entirely new business strategies.
Shipping before ordering. That's wild. Really shows the power of prediction. So how did these systems get so good? How did they figure out individual tastes so precisely?
Well, a lot of it came down to core ML techniques like clustering, methods like k-means clustering or Gaussian mixtures. These are ways to segment customers automatically, grouping people with similar behaviors or preferences based on their data browsing history, purchase history, demographics, etc. By understanding these clusters and your place within them, they could tailor the experience. And importantly, the success seen in deep learning for things like social media news feeds. Remember how they learn from collective behavior what we click on or comment on? Those same principles were applied to e-commerce, learning from your interactions to predict your interest, creating these really sticky, personalized experiences.
Ah, so the tech powering your newsfeed is related to the tech suggesting your next purchase. Makes sense. And that connection leads us naturally to advertising, another industry totally reshaped by ML's predictive power. How did AI change the ad game?
Advertising and marketing saw the potential very early on. They saw AI as a way to predetermine the horizon, as one source puts it. Basically, using ML to deeply understand consumer segments and define consumer brands for corporate infrastructure. It meant moving away from broad, one-size-fits-all campaigns toward highly targeted ads, delivering specific messages to specific individuals based on their predicted interests and behaviors. Much more efficient.
Right, no more generic billboard ads online. It became about pinpoint accuracy. But ML didn't just decide which ads to show us, did it? It started controlling all the content we see.
That's a crucial point. ML algorithms became the gatekeepers, deciding what gets amplified across platforms, not just ads. Your news feed, video recommendations, search results, algorithms curate all of it. And while this personalization is great for engagement, keeping you scrolling and clicking, it also created new and complex challenges, like the unintended amplification of problematic content. The algorithm doesn't necessarily know if something is true or harmful, only if it's engaging.
Amplifying problematic content. That sounds worrying. If the goal is just engagement, what are the risks?
This gets into some really subtle but significant harms. Ravi Iyer, a social psychologist formerly at Facebook, pointed this out. He noted how misinformation can spread implicitly. You take a true event, but the algorithm amplifies it in a way that suggests it represents a much broader pattern than it actually does, creating a misleading narrative. It's not necessarily outright lies, but a distortion through amplification. And beyond misinformation, think about content that's not harmful by itself, but because of the effect it generates in some people.
Sure.
His example was Instagram selfies, potentially having a devastating effect on teens' mental health by encouraging social comparison. The algorithm isn't trying to harm anyone, it's just optimizing for engagement, but the downstream effects can be really negative and complex.
Wow. So the very act of personalizing and optimizing for engagement can inadvertently cause harm or spread misleading ideas. That's a heavy implication. Okay, let's ground this in some concrete examples. Let's look at some iconic case studies that really show ML flexing its industrial muscle. First up, maybe the unsung hero of the early internet, the spam filter.
Ah, yes, the humble spam filter.
Yeah.
Probably one of the earliest, most widespread, and genuinely useful applications of industrial ML. It had a massive impact on just making the internet usable day to day, saved countless hours, prevented scams. Before ML, spam filtering was pretty basic, mostly keyword lists, easy for spammers to get around.
Totally take it for granted now, but yeah, I remember email being almost unusable before good filters came along. So what was the ML magic that made them so much better? How did they learn to tell spam from ham, as they say?
The big shift was moving from fixed rules to statistical learning. Spam filters use natural language processing, often relying on n-gram word models. N-gram is just a sequence of n words or characters, like buy now is a 2-gram bigram, make money fast is a 3-gram trigram. The filter learns the statistical probability of seeing certain n-grams in spam versus legitimate email, ham, And crucially, these were supervised models. They needed data labeling. That means humans initially had to mark emails as spam or not spam, providing the training data for the algorithm to learn these patterns. You clicking mark as spam was actually helping train the system. It perfectly fits that idea from communication theory. The goal isn't saving energy, it's accurate reproduction of a signal, getting the good emails through, filtering the noise.
Right, using our own actions to teach the machine. Clever. Okay, next case. Personalization at scale, the recommendation engine. We think Netflix now, but the core ideas were taking root in the 2000s. How did it get so good at guessing what we want to watch or buy?
Exactly. While maybe Netflix perfected it later, the principles were definitely emerging then. You see it discussed in the context of e-commerce and social media feeds, learning from collective behavior. The core challenge is accurately forecasting what particular customers want, moving beyond search to anticipating their wants. It's about building this incredibly detailed profile of your preferences, often implicitly.
Implicitly, meaning not just based on what I explicitly rate or buy, but my other behaviors too.
Precisely. These systems often use concepts from reinforcement learning.
Mm.
Think of the algorithm, the agent, trying to maximize the amount of reward it receives over time. The reward here isn't money, it's your engagement. Do you click play? Do you watch the whole thing? Do you add it to your list? Do you keep your subscription? By analyzing patterns across millions of users, what sequences of actions lead to more engagement, the system learns to predict what you specifically are likely to engage with next. It's constantly learning from every interaction, refining its predictions to keep you hooked.
Keep the user engaged, maximize that reward. Makes sense from a business perspective. Now, for something that really blew people's minds and showed ML could do more than just recommend movies, DeepMind playing Atari games, that felt different.
Oh, absolutely. DeepMind's work, particularly leading up to the Google acquisition around 2013, was a landmark demonstration that deep learning methods could significantly outperform people on complex strategy-based tasks. It wasn't just pattern recognition anymore. It showed that these systems could learn goal-oriented behavior in dynamic environments. It was about learning how to achieve something.
I remember the buzz around that. Which game was it that really caught everyone's attention? The one that made people like Larry Page take notice?
The really iconic one was the Atari game Breakout. The paddle and ball breaking bricks. The amazing thing was, they didn't tell the AI the rules or how to play. It just got the raw pixels from the screen and the score as input. And through reinforcement learning, trial and error, essentially it figured out strategies. The source describes how, within about 2 hours, the system had learned to knock the ball into exactly the right spot, to tunnel behind the bricks and wipe them out efficiently. A strategy many human players never discovered. This wasn't pre-programmed, the AI discovered it. That deeply impressed people like Larry Page. It was proof that ML could learn from interaction, learn from its own experience, without needing labeled examples. That demonstration really fueled investment and belief in AI's broader potential.
Wow, learning a novel strategy from scratch just by playing. That is impressive. And taking that idea of learning from interaction into the real physical world leads us to self-driving cars. Like Waymo, that's ML as critical infrastructure with huge safety implications.
Precisely. Waymo is a fantastic example of ML integrated into safety-critical, real-world business infrastructure. When you hear they've driven well over 20 million fully autonomous miles on public roads.
Yeah.
That's not a lab experiment. That's a serious deployment requiring incredible reliability and continuous learning in unpredictable environments.
20 million miles is staggering. How do they possibly train these systems to handle the sheer unpredictability of real roads? Pedestrians stepping out, weird construction zones, sudden downpours.
It's a combination, a mutually reinforcing loop between real-world experience and highly realistic simulators. Driving in the real world is crucial because it exposes the AI to the unexpected, the situations that engineers might never anticipate, the weird edge cases. But then, when the AI struggles with a real-world situation, maybe it hesitates or makes a suboptimal move. Engineers can take that exact scenario and recreate it in simulation. There, they can fine-tune the AI's response, running that tricky situation thousands or millions of times virtually, tweaking the algorithms until the car handles it perfectly. Then they deploy the improved model back into the real world. It's this constant cycle of real-world testing and virtual refinement that builds robustness.
That makes sense. Learn from the real world, practice, and perfect in the virtual world. A powerful combination. So we've seen these applications. Let's peek under the hood a bit more. How did the deep learning actually work? What made these algorithms learn so effectively?
Well, Yoshua Bengio describes deep learning very intuitively. He calls it a scientifically inspired approach, featuring layered structures that progressively represent more abstract concepts.
Think about how we recognize things. First, maybe simple lines and edges. Then those combine into shapes. Shapes combine into parts, like eyes or wheels. Then those parts form the whole object, a face, a car. Deep learning layers work similarly. The first layers might detect simple features in the data, like edges in an image or specific frequencies in audio. Subsequent layers combine these simpler features into more complex ones, textures, shapes, simple objects. And the deeper layers combine those into even more abstract concepts. It's this hierarchical processing that allows them to grasp really complex patterns.
Layers building up complexity, from simple features to abstract ideas. Got it. But how does the network actually learn the right features at each layer? How does it adjust itself? You mentioned gradient descent earlier. Right. Gradient descent is the workhorse optimization algorithm. The analogy is trying to find the lowest point in a valley while blindfolded. You feel the slope where you are, and you take a step downhill. Mathematically, the slope is the gradient of the loss function, how much the error changes with small adjustments to the network's parameters or weights. Gradient descent calculates this gradient and nudges all the weights in the network slightly in the direction that reduces the error the most. You repeat this step over and over, gradually descending towards a point where the network makes the fewest mistakes.
Okay, step by step downhill to minimize errors. But with massive data sets, taking one tiny step for each data point sounds incredibly slow. How do they speed that up for industrial use?
You're spot on. Processing one example at a time, stochastic gradient descent can be slow. So in practice, everyone uses mini-batch gradient descent. Instead of one example or the entire dataset, you calculate the gradient using a small batch of examples, maybe 32, 64, 128. This gives a pretty good estimate of the true gradient, but it's much faster to compute. And crucially, modern hardware like GPUs is brilliant at processing these batches in parallel. You can do the math for all 64 examples simultaneously. This efficiency boost is why mini-batch GD became the de facto standard in deep learning practice. It hit the sweet spot between accuracy and speed.
Parallel processing on small batches makes sense for efficiency, but how do you stop the model from just memorizing the training data? If it only learns the exact examples it saw, it won't work on new data, right? That overfitting problem.
Overfitting is a huge concern. A model that just memorizes the training set is useless in the real world. So several techniques were developed to ensure robustness and prevent this. Two big ones are L2 parameter regularization and dropout. L2 regularization basically adds a penalty to the loss function for having large weights in the network. It encourages the model to find simpler solutions that rely less on any single connection, which tend to generalize better. Dropout is clever. During training, it randomly ignores or drops out a fraction of the neurons in each layer for each batch. This forces the network to learn redundant representations, making it less reliant on specific neurons and more robust to noisy or unseen data. There are also things like automatic hyperparameter optimization algorithms that help find the best settings for these techniques without tons of manual trial and error.
So, building in checks and balances to force the model to learn general patterns, not just memorize, makes sense. And one last technical bit. These models can get huge. How do you actually deploy them efficiently? Especially on, say, a smartphone.
Yeah, model size and efficiency are critical for making these things practical in practice and not just academic curiosities. This is where model compression and optimization techniques come in. A really important one is quantization. Most models are trained using high-precision numbers, like 32-bit floating point. Quantization converts these weights and calculations to lower precision, maybe 8-bit integers. This drastically reduces the model size and memory and speeds up calculations, often with very little loss in accuracy. Using 8-bit math instead of 32-bit can provide tremendous speedups and huge energy savings during inference because you're moving less data around. That's crucial for running AI on edge devices or handling massive scale in the cloud.
Okay, so incredible technical progress made ML feasible for industry. But as it became woven into finance, healthcare, commerce, everywhere, it wasn't all smooth sailing. This integration brought serious challenges and ethical questions too, right?
Absolutely. As ML moved from the lab into real-world decision-making, the issue of bias in AI quickly became recognized as a significant issue. And it's usually not that the algorithm itself is intentionally biased. The bias almost always comes from the data it's trained on. If the historical data reflects societal biases, racial, gender, socioeconomic ordinance, the AI will learn those biases and potentially perpetuate or even amplify them. This can lead to real allocative harms, like unfairly denying loans or job interviews to certain groups, or representational harms, like search results reinforcing stereotypes. The AI just learns the patterns in the data it sees.
That's deeply concerning. The AI reflecting and even amplifying our own societal flaws and connecting back to the black box problem. If we don't understand why the AI is making a decision, it's even harder to detect or correct that bias, right? Exactly. Judea Pearl really highlights this. He criticizes deep learning's data-centric approach for producing opaque models that cannot explain their reasoning. These models often lack the ability for counterfactual reasoning. You can't easily ask, what if this factor were different, to understand the decision drivers. This opacity makes it incredibly difficult to audit for fairness, to ensure accountability, or for individuals to meaningfully challenge decisions made about them by an AI, especially in critical areas like hiring, credit, or justice.
So biased data can create unfair outcomes, and opacity makes it hard to fix. That's a troubling combination. What about the impact on people's jobs? The whole robots taking our jobs fear. Did ML's rise fuel that? It certainly did. The implications for labor became a major discussion point. Some argue that, like the Industrial Revolution, technology creates new, often better jobs. People shifted into better-paying jobs where they use their minds more. But others worry this time is different. As one source puts it, now, we're gradually figuring out how to replace our minds by machines, automating cognitive tasks, not just manual ones. And there's also the hidden human labor behind AI. The sources mention the labor exploitation that is at the core of the way generative AI is built. This refers to the often low-paid, precarious work of data labeling and content moderation, primarily in the Global South, that's essential for training these sophisticated systems.
Right, the invisible workforce cleaning up the data that fuels the AI. That's a crucial point often overlooked. And there's another invisible cost too, isn't there? The environmental impact. These massive AI systems must require huge resources.
They absolutely do. We need to talk about the gigantic extractive infrastructures behind AI. Training large models requires enormous data centers, which consume vast amounts of electricity and, critically, water for cooling. There are documented cases like the one cited concerning Google and Cerritos, where local communities face resource depletion, plundering precious water to support these data centers. It really highlights the planetary costs of artificial intelligence. The digital world has a very real, very physical footprint, often with significant environmental and social justice implications.
Water scarcity driven by data centers. That's a stark reminder of the physical reality behind the cloud. And finally, looping back to the amplification issue we discussed with ads and social media, that seems like a persistent ethical minefield.
It really is. Recommendation algorithms, designed to maximize engagement, inherently risk amplifying problematic content. And it's often subtle, exploiting the gray area inherent in any content moderation policy, like taking a true event and presenting it out of context to misinform people implicitly, suggesting it's part of a broader, perhaps non-existent pattern. Because this kind of content can be highly engaging, the algorithms may push it widely, contributing to polarization, echo chambers, and the spread of harmful narratives, even without intending to. It's a fundamental challenge tied to the optimization goals of these systems.
Okay, so looking back, it's clear the 2000s were absolutely pivotal. Machine learning stepped out of the academic shadows and became this, well, invisible but essential infrastructure for modern business. We saw it transforming finance, healthcare, e-commerce, advertising, impacting everything from fraud detection and medical diagnosis to your shopping cart and newsfeed. It really showed its practical power, turning sci-fi concepts into everyday tools.
Definitely a transformative era. But as we've discussed, that integration wasn't without its complexities. It surfaced these really profound questions about bias in the data, the lack of transparency in the models, the impact on jobs, and even the environmental cost. That leap into industry was just the beginning of grappling with these deeper implications.
Absolutely. And as ML continues its relentless march, embedding itself even deeper into our work, our society, our personal lives, that initial sense of awe is maybe giving way to a more critical understanding. So perhaps the provocative thought to leave you, our listener, with is this. How much further can machine learning integrate into our lives before we, as a society, need to fundamentally rethink things? Not just how we use these powerful systems, but maybe even who we are in relation to them. What does it mean to coexist with increasingly intelligent machines?